Hello, everyone. I'm back. It's your second favorite professor, Evan Donald. I'm going to turn off my video now. I just noticed that was on. I really only want you guys to see the whiteboard. There we go. Now you don't have to look at my face. I hope you are all doing well in isolation. Hope everyone's staying healthy. I just got some equipment in the mail, so that allows me to use this whiteboard with a stylus. So I'll now be able to produce some slightly better versions of the material than what I was capable of before. I've been relying on my colleague Ariel, her videos for the chapter 11, and they're great, and you can continue using them. I'll continue linking them in web courses. If you miss my lovely voice and want to hear me lecture, then you can watch these. They'll both be in the same, I'll put them both in modules on web courses, and let you guys decide what you want to use. All right, so where are we? We are in chapter 11. So let's just kind of recap what we've done so far. Hopefully you guys have watched the preceding videos for sections 11.1, 11.2, 11.3. Okay, so let's see where we're at. Since I haven't talked to you guys in a while, recap. Okay. 11.1, we introduced sequences. 11.2, we introduced series. Okay. So let's see, what does a sequence look like? Something like this, an ordered list of numbers. Okay, what does the series look like? Now we're talking about an infinite summation. Okay, so we're adding up an infinite amount of numbers, an, all these ans. And remember the connection between sequences and series. When we're asking, we can ask whether sequences converge or not to a number, to a limit. And we can ask the same thing about series by considering the sequence of partial sums, where we say we let Sn equal the sum from 1 to n of my numbers, okay? So I'm adding up numbers here, and that gives me a sum, Sn, at each step n. And then I'm looking at this sequence, and I'm asking if this sequence converges to a limit using the tools we developed in section 11.1, okay? And that introduced the major question for series, where whenever we see a series, our most important concern is whether these series converge or diverge. Converge meaning, does it go to a finite number? Diverge, does it go off to infinity or just maybe alternate, something like that, where it doesn't settle in on a single number. Maybe it flips between 0 and 1, 0 and 1, 0, 1. So it never converges, okay? Remember, when we're talking about convergence, we need it to go to a finite number and we need it to get infinitely close to that number and stay there, okay? And then if a series converges, then we can ask, okay, what is the sum of that series, okay? And we're not gonna ask this question for all series, okay? We ask this question for every series we deal with, okay? And then if the series is a nice form like a geometric series or a telescoping series, then maybe we can find the actual sum. But usually, we don't find the sum, just because, as you can imagine, finding out what the sum of adding up an infinite amount of number is could be quite difficult. It is really only possible if the series has a nice form like the geometric series and the telescoping series. Okay, so then what is the rest of this section about? What is the rest of this chapter about? It's really focused on this first question. Does the series converge or diverge? Okay, so in section 11.2, we saw geometric series and telescoping series. We saw how we can find their sums. And then the rest of these sections are just about this first question. We're going to ask whether series converges or diverges, and usually we're not going to bother finding the sum. Okay? And then, let's see, in 11.3, we saw the first example of that, the integral test. Okay? So this is the first of these sections where we introduce the integral test that just tells us whether this the series we're dealing with converges or diverges. 11.4, now we're going to introduce another test. Comparison test. So that's where we're at today. The comparison test is extremely powerful. It allows us to simplify some very complicated looking series into something much more simple and determine almost immediately whether the series converges or not. So I'll give you a motivating example first that shows you the power of these, and then we'll develop the theory a little bit more. Okay, so let's say I had the series let's make it something really complicated. Okay, 1 over all of this, and I'm adding this up. So 2 to the power n plus log of n plus 5 plus 6 times n. And I'm asking, does this series converge or diverge? Okay, so this is fairly complicated. But let's focus on this portion here. Okay, if I just looked at that, I would have 1 over 2 to the n. Okay, this is a geometric series, right? Maybe to make it a bit more clear, I could write it like this. Okay, so this is my ratio, my R term, okay, and that's less than 1. So my series should converge, and we could even find the sum if we wanted, but we don't need to do that right now. Okay, we do know this is convergent, right? Which whenever something's convergent, or it converges, we're saying it is going to converge to a finite value. So we can write less than infinity, strictly less than infinity. This is kind of shorthand to say that the series converges. Okay? Now, what about our original series, 1 over all of this? Okay, does this give me any information about this? Let's see. I know that, okay, I was trying to figure out how to scroll down in Zoom, but it doesn't look like it wants me to do that, so let's just move to a new page. Okay, I'll try and remember what I wrote. Let's see, we're considering this series. I don't believe I had that. Let's see. Yeah. Okay. And then on the other hand, we said, okay, that looks very similar to this series. Okay. And we know this series converges, okay? It's less than infinity. Now, think about these two numbers in the denominators, okay? Which is bigger? Okay. I have 2 to the n here and 2 to the n plus log n plus 5 plus 6n. Okay, for n in the natural numbers, okay, n being a number greater than or equal to 1. Missing some notation here. Okay. This should be greater than 0, and this should be greater than 0, right? Okay, if n is greater than 1. So this denominator is bigger than this denominator. So in this fraction, I'm dividing by a larger number than in this fraction. Okay, so it seems like we have this, right? Every number I add up over here is smaller than every number I add up over here. Okay, so that means, okay, that this entire sum should be less than or equal to this entire sum. And this sum is less than infinity. So I should be able to conclude that this is less than infinity as well, meaning it's convergent. Okay, so that's the idea. This is a very complicated series, and I can reduce it almost immediately just by looking at these terms here to something extremely simple. Okay, this is just a geometric series. And I know, maybe I know just in the back of my head that, okay, if I have 1 over 2, that's less than 1, so it's going to be convergent. This is convergent, which means that's convergent. So that's the power of these comparison tests. They allow us to turn very complicated series into very simple series. Now let's start building up the techniques we need to apply this kind of knowledge and get some practice in. Okay. The main difficulty, this is a difficult section for a lot of students, and I don't think it's necessarily the concept so much as working with the inequalities themselves. So let's first look at inequalities. Okay? Get a little practice in on those. Okay. Let's assume let's stick with this case. Okay. We have positive numbers A, B, and C. And let's start working with some inequalities of fractions. Okay. Let's say I have, and let's say I have the additional condition that, okay, where A is less than or equal to B. Okay. Let's look at these fractions. Okay. If A is less than or equal to B, okay, and C is the same in both, okay, the denominator is the same in both of these fractions, then I can see immediately that I should have A over C is less than or equal to B over C, right? So let's say A is 3 and B is 5 and C is 10, okay? So, to put a concrete example in there, I should have 3 over 10. I got, and on the other hand, I got, let's see, 5 over 10, okay? I can see that this inequality does hold. A over C is less than or equal to B over C. But now, what if I flip these fractions? Ah. Okay. Now, sticking with the assumption that A is less than or equal to B, I should have this, right? So 10 over 3 should be greater than or equal to 10 over 5. Why? The number in the numerator is the same, and this left side, I'm dividing by a smaller number. So the result should be larger than on this right side, okay? This is the key concept you need for comparison tests. We gotta have this logic, okay? And you don't necessarily need to have it just by looking at it. A lot of times, if I see a complicated, I deal with inequalities all the time. Sometimes if I have a complicated inequality, I take it very slowly. I take it step by step. So I'll be looking at, let's say I'm looking at the inequality. Let's say I'm looking at the inequality A over B and A over C. And maybe I don't understand right away which one's bigger. And then I take it step by step and I say, hey, okay, what's the relationship between B and C? I say, okay, B is less than or equal to C. And then I turn it into my fraction. I say, okay, A over B, and then I got A over C. Well, on this side, I'm dividing by a smaller number, okay? So that result should be larger than when I divide by a much bigger number. So I should have the inequality going this way. Again, this is assuming A, B, C, all positive. Okay. All right, so now let's see some more examples of things we might encounter in our series. Okay. How about 1 over 2 to the n plus 1? And what would we compare that to? Let's set that question aside for a second, and I'll kind of give you that for free. Let's compare it to 1 over 2 to the n. Okay. Which one of these fractions is larger? Okay. Well, I'm going to break it down step by step. Say the numerator is the same in both, and then I got 2 to the n plus 1 and 2 to the n. Well, let's see, this side is bigger, right? Because I'm adding a positive number to it. Okay. Now, what does that tell me about these fractions? Okay, on this side, I'm dividing by a larger number. Okay, so this fraction should be smaller than this fraction. Okay, so I should have my inequality going this way. Let's see another example. How about, this is in the notes, by the way, 3 to the n plus 5. Okay, okay, everything, oh. There's no n there. It's multiplied by n. Okay, let's see. All right, so everything's positive, numerator's positive, denominator's positive, everything's positive. We really want to confine ourselves to the case when everything's positive, okay? Numerator, denominator, everything's positive. Okay, so let's see, numerators are the same in both. On this left side, okay, what's going on the denominators? On the left side, my denominator is larger, okay? So I'm dividing by a larger number, okay, over on this left side. So again, I should have this. Okay. Where people run into trouble, okay, let's just rewrite what we had on the previous page. I said this, right? 1 over 2 to the n plus 1 is less than or equal to 1 over 2 to the n, because we're dividing by a larger number. But what about this? This is where people run into trouble a lot, okay? Now I'm subtracting a positive number away, okay? So this, let's, use, let's say n is greater than or equal to 1, okay? So we're not dividing by 0 or anything like that, okay? So let's see what's happening here. I'm dividing 1 by a smaller number than over here, okay? So I should have this. The inequality should be going the other way. 1 over 2 to the power n minus 1 is greater than 1 over 2 to the n, okay? This is a common mistake people make. They often have the inequality going the wrong way. Okay, so we got to be careful with these inequalities. We got to make sure we have the inequality sign going the right way. Okay, the comparison test is very sensitive to that. We got to be very careful. Okay, now let's go into the statement. Let's actually start talking about the comparison test. First, we'll start with the statement of the comparison test. Okay. Okay, so the statement of the comparison test has two parts. Let's focus on the first part. Suppose that an and bn are, the summation of an and summation of bn are series with positive terms, meaning all the ans are positive, all the bns are positive. Okay, so the first part of the comparison test states, if the summation of the bn's is, the series bn is convergent and an is less than or equal to bn for all n. Okay, so every an is less than every bn. Okay. Then the summation of the ans is convergent. The series is convergent as well. Okay. So how could we write that as an inequality? Okay. Well, let's see. We have series an, series bn. Okay. Let's see, what do we know? We know that this series bn is convergent, which we can indicate by writing less than infinity. Okay, and every single an is less than or equal to bn. Okay, so this series, if I add up all the ans, it should be less than or equal to when I add up all the bn's, right? And then since everything's positive, I could also have greater than or equal to 0 here. Okay, so my series an, just kind of condensing what I know about an, say an should be less than infinity, greater than or equal to 0. And what's really important here is that it's less than infinity, it's convergent. Okay? This series converges to a finite number. How do I know it's convergent? Well, let's see. We could think about the material in section 11.1, which you may or may not recall. let's see, this series, what do the partial sums of this series look like? Okay, let's consider the sequence of partial sums for AN. Okay. Say SN equals, okay. Since AN, all the ANs are positive, SN has to be getting bigger, right? Because I'm just adding positive numbers every time I add another sequence. So let's see. This is actually bad notation. I should have K here, not N. Okay. How could I write the n plus 1th partial sum of this series? I add up the first k term, or the first n terms, okay? I'm adding up all the a's from 1 to n, and then I tack on a n plus 1. Okay, that should give me Sn plus 1, right? This is a positive number, this is a positive number. So we can see that every time I increase this index here, I'm getting a larger number, okay? So equals the stuff up there plus an plus 2, right? Again, this is positive number. So Sn is growing, okay? Sn is growing. On the other hand, we know this Sn, this sequence of partial sums, it's got to be less than Bn, right? From the entire series of Bn, because it's, let's see, An is less than or equal to Bn term by term, okay? And this is some finite number, okay? So this is growing and it's bounded above by some finite number C. Okay? That's the concept of why this series AN converges. If that's too much, if taking it back to the partial sums is too much, that's a good concept to be able to execute or tie in with the future concepts. But if that's too much, just think of it like this. Okay, we got the series AN is less than or equal to this series, which is less than infinity, or it's convergent. So that means that this series has to be convergent as well. Okay, now let's see the second part of the comparison test, the statement of the second piece. Okay, the second piece of the divergence, or excuse me, the comparison test says, if the series Bn is divergent and An is greater than or equal to Bn for all n, then the series An is divergent as well. Okay, so how could we write this out? Okay. Let's say I have Bn, series Bn. Okay. And what am I told this time? I'm told every An is bigger than Bn. Okay. So the series An should be bigger than the series Bn. And let's see, the series Bn is divergent. Okay, since Bn is all the Bn's are positive. Okay, that means this series is going to infinity. Okay, so I could write that like this. So what does that tell me about my series An? Okay, just to recap, I have So that means my series AN is greater than or equal to infinity, meaning this is, again, a way of writing that the series AN is divergent or diverges. Okay. Again, tying it back to this idea that if this series Bn diverges to infinity and An's always bigger than Bn, then the same has to be true for the series An as well. We have to be careful with the comparison test because it's very specific in how it can be applied. We have to look exactly at what it's saying and make sure our series that we're comparing satisfy these criteria exactly. So read these over and make sure you understand exactly what they're saying. Okay, now let's see some, we'll talk about what they don't say later. Okay, maybe that'll be a bit clearer. But first, let's look at some applications of this. Okay. So now let's try and use the comparison test on some series. So let's start with one over n squared plus one. Another difficulty with the comparison test is figuring out what to compare to. Okay, so I'm given this series. What does it look like? What would be the simplest form of this I could get with some ignoring some terms? Okay, this looks a lot like this series. Okay, what do I know about this series? This is a series you can use, let's see, the integral test on and the p-test, right? Okay, so I have 1 over n to recall the p-test. I have 1 over n. Oh, that's horrible. When I have 1 over n to the power p, and p is greater than 1, then the series is convergent. Okay, so now let's look at this, or we could do this by integral test by integrating 1 over x squared. Okay, so by the p-test, this series is convergent because my p is equal to 2, which is greater than 1, so it's convergent. What does that tell me about the convergence of this series here? Okay, so let's call this my series AN, and let's call this my series BN. And now let's go back to the statement of the comparison test. Okay, let's see. Bn is convergent. If Bn is convergent and An is less than or equal to Bn for all n, then the series An is convergent as well. Is that what we have here? Okay, this is my series Bn. We know that this is convergent by p-test. Okay, so this is convergent. My Bn is convergent. Now, let's look at my terms here. Let's look at my ANs and look at my BNs. is 1 over n squared plus 1 less than or equal to 1 over n squared? Yes, yes it is. I'm dividing by a larger number on the left. So that means this fraction is always less than or equal to this fraction. Okay. So what should I have? I should have this inequality here, which I can simplify to this. The series 1 over n squared plus 1 is less than infinity, meaning, okay, this series is convergent. Okay. Now, that's the logic behind this problem. I'll show you very quickly just how I would write this problem out. Let me write out the steps for using comparison test to show a series is convergent. Okay, so let's say we start with a series AN. Okay, and we want to show it's convergent by comparing it to BN. I'll talk about how to figure out what to compare it to in a moment, but let's talk about these steps first. So we have series AN and we're comparing it to BN. Okay, what do I do? First, I should verify that these series have all positive terms. The statement of my comparison test says that my series have positive terms. Okay, so suppose the series AN, series BN are series with positive terms. So everything needs to be positive. Usually that's pretty easy to check. For example, I have the series, going back to the example we were just working on, I have this. Okay, maybe it's as simple as saying 1 over 2 to the n plus 1 positive for all n, and 1 over 2 to the n positive for all. This is more what you would do if you were writing out a test. For your homeworks, it doesn't usually ask you to do this, but it's a good first step to keep in mind. We need to verify that all the terms are positive. Okay. Next, I need to show AN is less than or equal to BN for all n. Okay, again, this is usually fairly straightforward. Going back to that previous example again, you would say 1 over 2n, you're comparing 1 over 2n plus 1 and 1 over 2n. You say, maybe note 2n plus 1 is greater than or equal to, is greater than or equal to 2 to the n. So again, this is something you would do on a written test. Finally, you say, since Bn is convergent, An convergent by comparison test. Again, this is very important, and might be something you guys are missing out on by having the online classes from now on. But in previous semesters, if you don't have these steps, the question's wrong, even if you come to the correct conclusion, and even if we know you've used the comparison test correctly, if you haven't gone through these steps, then you really haven't done it correctly, because the comparison test relies on the fact that the ANs and BNs are all positive, that AN is less than or equal to BN, and then finally, on the assumption that BN is convergent, we have to say by comparison test. Whenever we use a test, we have to name the test we're using. We can't just assume that the grader or the professor, instructor knows what test we're using. We have to state it explicitly. Again, that might not come up on homework, but very important. So applying that to our problem, we had 1 over 2 to the n plus 1. Okay, so to do this problem, I would say compare to this series. First, I would say, okay, A and Bn are positive for all n. And I guess I should be clear about what my An and Bn are. Okay. 2. Okay, again, we have 1 over 2 to the n. Okay, is less than or equal to 1 over 2 to the n. And finally, let's say note 1 over 2 to the n convergent. And it's also good to say why this is convergent. Okay, why is this convergent? You could say by p-test or integral test. So if I was writing out this question, this is how I would write it out. And just to be clear, maybe the question, I didn't actually write the question down. Okay, maybe the question was test 1 over 2 to the n plus 1 for convergence. All right, let's see another example. Now let's use part 2 of the comparison test. Let's show something's divergent. So let's say I have, I'm gonna mark this one example. Okay, let's say I want to test natural log of n. Actually, let's start at why am I starting at 3? That's a little technicality I'll discuss later. It's nothing too important. All the same rules apply. Okay, let's test this series for convergence or divergence. Okay. So let's test this series. First of all, let's start talking about how we determine what to compare our series to. When I look at a series and I'm asking myself, okay, what do I compare it to? I look at it's usually a fraction, or not necessarily, but I look at my terms and I say, okay, how could I simplify this? What would be how could I make this the simplest version of itself? Okay. So I look at ln of n over n, and I think about, let's see, what if I just had 1 over n? Okay, that's simpler than ln of n over n, right? The harmonic series. And remember, this is our most famous divergent series. We're going to use this a lot with comparison tests. It's a great series to compare things to if you want to show something's divergent. Okay. So let's see. I know this is divergent. This, again, using this little shorthand for divergent, we're going to say this goes to infinity. Okay. All right. What do I know about how do 1 over n and ln of n over n compare? Okay. Well, let's see. We're starting at 3, right? Okay. So if I'm starting at 3, if I plug 3 into ln of n, let's see, 3 is a bit bigger than e, right? Okay, so ln of 3 should be a bit bigger than 1. Okay, and as my n increases, ln of 4, okay, that's bigger than 1 as well. And it's going to continue that way forever. The bigger, remember what ln of the graph of ln of n looks like. Let's see, it goes like this. It's increasing, right? Okay, so I'm starting at 3, 3's around here, maybe 1, okay. So ln of 3 is a bit bigger than 1. Okay. All right. And it's increasing from there. So as I move farther to the right, my graph of ln is going up to infinity. Okay. So what does the inequality look like? Denominators are the same. The numerator over here is bigger, which means I have the inequality going this way. Okay. Now, so that should indicate okay, and I know this series is divergent. So that means this series is divergent as well. Okay, so now let's write this up formally. Let's see, first I'm going to follow very similar steps. The first 2 steps should be identical to showing convergence. Okay, so first I verify all positive. Let's see, 1 over n. Okay, I can just say it's clear that, okay, this is is positive. It's clear that 1 over n is positive for all n. Technical difficulties. Okay, 1 over n is positive for all n, and ln of n, let's see, when is this? It's positive. When is this positive? Well, if n is, let's see, 1, this would be 0. Okay, well, it's positive for all n greater than 1. Okay, and remember our series was starting at 3, right? All right, 2. Now we need to verify that, let's see, what do we want to show that 1 over n is less than or equal to ln of n. That's what we're going for, right? Okay, let's see. We could say ln of n is greater than 1 for n greater than or equal to 3. So 1 over n is less than or equal to ln of n over n for n greater than or equal to 3. Okay, part 2 done. Okay, now just to sum up, I would say 1 over n divergent. Why is this divergent? Well, if we wanted to be thorough, we could say by p-test, or we could say the harmonic series is divergent. Mention harmonic, maybe. And then, so ln of n over n divergent, again, by comparison test. So that is how I would write out that question. Okay, so let's recap how to use the comparison tests. Okay. Let's write these steps down again, and now instead of just showing for convergence, let's kind of keep them general. Okay, 1, verify all terms positive. Okay. 2, show the inequality. We could say show the inequality holds. Boom. So we need, let's see, we either need to show an is less than or equal to bn for all n, or we need to show an is greater than or equal to bn for all n. And then 3, can say cite the comparison test. So let's see, if we started with a series an and we're trying to show it's divergent, then we need to show, okay, an's, bn's are all positive. Then we need to show an is greater than or equal to bn. And if we know bn is divergent, maybe we have to show that as well. Maybe we have to show bn is divergent, okay? But we show this inequality holds, this is divergent, and we say, okay, by comparison, and divergent. Okay, so those are the general steps. Now let's talk about what we can't do with comparison test. Okay, so let's clear that. What if I had this series? Okay. Let's think about what we would compare it to. Okay, what would we compare it to? Again, I'm trying to make this as simple as, I'm trying to boil this down to its kind of simplest cousin, if you want to say. Okay, what does this kind of look like? Well, this looks similar to this series. Okay. 1 over 2 to the n. And let's see, what do I know about this series? This is a convergent geometric series, right? So I might be tempted to say that this series converges as well. And maybe it does. Let's see, does it? It should. But can I use comparison test? No. Let's see, why not? I can't compare these two series at the least. Let's see, I'll go through my steps. Okay, I verify, let's see, verify that they're all positive. Yeah, all A and B N positive. All A and B N positive. That's no problem. Okay. 2, this is where we get into trouble, the inequality. Let's see, to show that this series is convergent, what would I need? I need 1 over 2 to the n minus 1. Let's see, I need this, right? Okay, but I don't have that. The inequality actually goes the other way. 1 over 2 to the n minus 1 is greater than or equal to 1 over 2 to the n. I'm dividing by a smaller number over here, which means this fraction should be larger than this fraction. Okay, so really, I don't know anything. I can't, this series doesn't tell me anything about this series because the inequality is going the wrong way. So let's see, comparison fails. So how can I restate this? If I have series AN and series BN, okay, let's say that this is convergent. Okay, and then the inequality is going this way. Okay, what do I know about the series AN? I don't know anything. Okay, so if BN is convergent but AN is greater than or equal to BN, I don't know anything about this series. It could be convergent or it could be divergent, okay? We have to be very careful on how we interpret this, okay? On the one hand, just because I have the series AN as greater than the series BN, that doesn't mean that this is divergent, but we don't know that it's convergent either. So we know nothing, okay? We can't say divergent or convergent, okay? So what do we do? Well, we would have to compare to something else or use a totally different test, okay? So need more work. Okay. So we don't know anything about AN, we have to do something else. We have to use some other test. We have to compare to some other series, all right? So we have to be very careful. And then on the other hand, let's say I had some AN and some BN. Let's say I know it's not, let's say I know this series BN is divergent and I have this inequality, okay? Again, I know nothing about sum of AN. Just, okay, this goes to infinity, but sum of AN is less than or equal to this, okay? So this could go off to infinity, or this could converge to a finite number. This could be a convergent series. So it could be either. Again, we need more work. Okay. So going back to the original statement of the comparison test, we have to be very careful how we interpret it. We have to interpret it very strictly. Okay, so AN, suppose these series are series with positive terms, all the ANs and BNs are positive. If BN is convergent and AN is less than or equal to BN for all n, then AN is convergent. If BN is divergent and AN is greater than or equal to BN for all n, then AN is divergent as well. So you can think of it as there's 4 possibilities, right? Let's clear this. Okay. Okay, I have AN, BN. Let's say I have these series. There's 4 possibilities, right? Let's see. I could have this, or I could have this. Okay, so that looks like 2. But then, okay, let's say there's 2 for each of these. Okay. What if BN is convergent? And what if it's divergent? And again, there's 2 possibilities here. Excuse me. I'm getting used to this stylus. Okay, so there's these 4 possibilities, right? Okay, well, we know something about AN if we have this possibility. AN is less than or equal to BN, BN's convergent. All right, we know something. Okay, what if BN's divergent? We don't know anything. And again, if the inequality is going this way, okay, if BN is convergent, we don't know anything. If BN's divergent, we do know something. Okay, so these are the cases covered by the comparison test. All right. Before we move on, let's just talk a little bit more about finding out how we find out what to compare our series to. Okay, let's see. A very common example or very common form you guys will see is comparing things to P series. Okay, so let's say I'm given this series. Okay, let's see. What should I compare this to? Well, if I had 1 over n to the 5th, that would be a P series, right? That's convergent, okay? And I should have this series on the left is less than or equal to this. So that would mean this is convergent as well by comparison test. How do I find that? Again, I just look for this, to boil this down to its most simple form. Okay, why did I pick 1 over n to the 5th, not 1 over 3 to the n, 1 over 9? It takes a little practice, okay? If I compared this to, let's see, if I had compared it to the sum 1 over 3 to the n, the inequality still holds, right? The inequality still holds, but all right, now, this is not 3 to the n, it's 3 times n. Excuse me. There we are. So as I was saying, it's 3 times n. This series is divergent, and then I have this series on the left is less than or equal to this. So that tells us nothing. This is one of the cases that tells us nothing. So I have to pick something. I have to pick something to compare my series to that's going to satisfy my inequality and give me some new information. Okay. Again, it's just a matter of practice, really figuring out what to pick. But there are some techniques that can help us make this a bit easier. Okay. So let's say I have, and this technique will be important on the limit comparison test as well. Let's say I have polynomials on top and bottom. Maybe I have okay. Maybe I have something like this. Again, figuring out, just looking at this to figure out convergence or divergence, that might be difficult. Let's try and use comparison tests. Okay, so I want to, again, simplify this as much as possible. I'm going to look at the highest powers on top and bottom. Okay, so let's see, I got n to the 4th. Oh, and on the bottom, I got n to the 6th, okay? Now this equals 1 over n squared, right? All right, this series is convergent by p-test. And do I have an appropriate inequality here? Okay, let's see. What do I know about n to the 4th over n to the 6 plus 7n plus 1 and n to the 4th over n to the 6? Okay, which is bigger? Well, let's say on the left, I'm dividing by a larger number, so I should have the inequality going this way. Now, let's go through the steps of our comparison test. Okay, yeah, for n greater than 1, greater than 1, all positive terms. 1, 2, verify the inequality. All right, yeah, for I'll just say, you know, it does hold, okay? In a lot of cases, this is going to be very obvious. So yeah, inequality holds. Okay. And then 3. So our series n to the 4th over n to the 6th plus 7n plus 1 converges by comparison test. So really, when we're trying to compare our series to something, we really want to boil it down to its most simple form, okay? And that's what we compare it to. One more example, then we'll move on to the limit comparison test. Let's say I have okay, let's start it at 2. If I had started at 1, I would have division by 0, so let's start it at 2. Let's say I want to test this series for convergence. Okay, well, again, let's simplify. What's complicating things? If I just had 1 over to the n, I would have the harmonic series, right? Okay, so let's see. I'm going to try and compare it to the harmonic series. It's very close to what I have going on over here. Okay, let's see. I know this series is divergent. How does this series compare? Well, 1 over n minus 1 is greater than or equal to 1 over n, right? Okay, so that's my inequality. So the same should be true for series. Okay, so n greater than or equal to 2. I have 1 over n minus 1 is greater than or equal to 1 over n. So I should have this. This series is divergent. This series is greater. So this series should be divergent as well. So I say, so there we are. All right, let's move on to the limit comparison test. The limit comparison test is closely related to the comparison test. And limit comparison test is great because we can use it when we're, let's see, how shall I say that? I'll say it like this. We can use when the inequality is going the wrong way. Okay. It's kind of a informal way to say this. So what does that mean? I gave you the example earlier, this series. And we tried to compare it to the geometric series 1 over 2 to the n, okay? But the inequality was going the wrong way. We know this converges, but to show that this converges, we would need that. But that's not true. It's actually the other way, okay? So the inequality is going the wrong way, but they're still very similar. So the fact that this converges really makes me think that this should converge, okay? How can I show that? That's when I'm going to use the limit comparison test. Okay, so a little motivation. Now let's move on to the actual statement. Okay, here's the statement of the limit comparison test. If the series AN and BN both have positive terms, and if the limit as n approaches infinity of AN over BN equals C, where C is greater than 0, strictly greater than 0, and less than infinity, then either both series converge or both diverge. Okay, so that's a little weird, a weird statement, but the application of this is really straightforward. Okay, so what I do is I look at the terms inside each series and I consider their limit, the limit of their ratio. Okay. And if the limit is some positive number, like 0.5, 100,000, 9, it doesn't matter what this number is, as long as it's a number greater than 0 and less than infinity, then both series have the same behavior, okay? We can think about it like this, that if their limit goes to a finite number, then their behavior is pretty much the exact same. It's only different by a constant you could think of. Convergence of series, divergence of series, it's really about the behavior of the tail. Okay, so this limit is saying the limit of AN and the limit of BN are doing something very similar, but maybe it's different just by a constant. Maybe the limit of AN is 2 and the limit of BN is 4. Okay, so the C would be 1/2, something like that. As long as it's a number larger than 0, this will hold. Okay. If the limit was 0, what would that say? It would say that the limit of BN, this limit of BN goes, let's see, limit of AN decreases a lot faster than BN. Okay, so that would, to think about it like this, okay, the tail of AN is a lot smaller than the tail of BN. So maybe AN's convergent, but that doesn't necessarily mean BN is convergent. Okay, so that's why we need C greater than 0. And then infinity is similar. So now let's see an application of this. Let's go back to that problem we couldn't handle earlier. Let's consider this series again. Okay. Again, I try and compare it to something, but what I'm comparing it to is 1 over 2 to the n. My inequality is going the wrong way. Okay, this is convergent, but that doesn't tell me anything about this. Okay, so the inequality is going the wrong way. So that makes me think I need to use a limit comparison test. Okay, so let's say that this is my AN and this is my BN. What does my limit comparison test say? Okay, I'm going to do AN over BN. Okay, so I'll do 1 over 2 to the n minus 1 over 1 over 2 to the n. Okay, let's simplify that. What is this limit? 2 to the n over 2 to the n minus 1. maybe just by looking at it, you can tell that this limit is equal to 1. Okay, so my C is equal to 1. Let's go back to the statement of the theorem. Okay, we have our series, our terms are positive. We have limit of an over bn equals 1. Okay, and 1 is greater than 0 and it's less than infinity. So what does my theorem tell me? It tells me that my series have the same behavior. Okay, how does that help? Well, I know this series converges. 1 over 2 to the n, that's a convergent geometric series. Okay. My C is 1. Okay. So that means this series converges as well. Okay. So now let's see how to write that out clearly. Okay. So maybe I was given this question, tests 1 over 2 to the n minus 1 for convergence. Okay. How do I go about this? Well, we need to verify, again, we need to verify AN and BN are positive. Okay. Maybe at this step, I already know I want to compare it to 1 over 2 to the n. Okay. So I've verified that this and this are positive for all n. Okay. Then I find limit of AN over BN. Okay. We said that was equal to 1. Okay. And then if C is greater than 0, less than infinity, series have same behavior. So since this converges, our original converges by limit comparison test. Again, I should state the name of the test. All right, let's see one more application of the limit comparison test. I have several examples in my lecture notes, my written lecture notes, so check those out. Let's use this example. This is the second one I did at the end of the notes. Let's test this series for convergence or divergence. Okay, what does this series look like? Let's see. Well, the denominator is n to the power 1 times n to the power 1/2. Okay, so I could just rewrite this as this. Okay, and now what should I compare this to? Maybe I want to try and use the standard comparison test first. Okay, well, this looks like n over n to the 3/2, which would be, let's see, n over, that would simplify as this, n to the 1/2, which is square root of n. Okay, and then how does that compare with this? Well, let's see. Actually, you know what? To make it a bit clearer, I'm going to write this as that. Okay. Now maybe it's obvious that this diverges by p-test. All right, how does that compare? Well, actually, we don't even need to do a limit comparison test for this because my original is greater than this, right? Let's see. My original n plus 1 over n to the 3/2 is greater than n over n to the 3/2. Okay. So I don't even need limit comparison test. I could use limit comparison test though, couldn't I? Okay. So I know this diverges by comparison test. All right, let's find one that I have to use limit comparison test on. Okay, I think this is a good one. N to the 5th minus 1 over n to the 6th. All right, let's try and figure out something to compare this to. All right, if I got rid of the 1, I would have n to the 5th over n to the 6th, and that would simplify as 1 over n, right? I could simplify that to 1 over n, or I could consider it should work out the same if I do n to the 5th over n to the 6th. Shouldn't matter. All right, so I could use either one of these. Let's use this one. Okay, so I'm going to compare my series to 1 over n. All right. Can I do the straight comparison test? Well, let's see. I know this is divergent, but this series is less than or equal to this, right? Less than or equal to what I have is I have n to the 5th minus 1 over n to the 6th. That's less than or equal to, we'll just stick with n over 5 over n to the 6th. It's clear, right, that this fraction is less than or equal to this because I'm subtracting a positive number up top. Okay. So the inequality is going the wrong way. This is divergent. That doesn't tell me anything about this with the standard comparison test. What I'm going to do is I'm going to use the limit comparison test. Okay. So I'll say an is my n to the 5th minus 1 over n to the 6th. Bn is, let's say this. Okay. What is an over bn? Okay. Multiplying by the reciprocal, that would be this. Now, what is the limit as n goes to infinity of an over bn? What is the limit of this? Remember, computing limits, when I have powers, I want to look at the highest powers, the coefficient in front of the highest powers, all right? So let's see, I have n to the 11th on top, n to the 11th on bottom, coefficient 1, 1. So the limit should be 1, all right? And let's see, 1 is greater than 0, less than infinity. So the rules of the limit comparison test tell me that these series are going to do the same thing. Whatever they do, they're going to do the same thing. All right. So let's see. We're looking at this one. We know this series diverges because it is equal to the harmonic series. All right. So this one diverges. By limit comparison test, we know they both do the same thing. So n to the 5th minus 1 over n to the 6th diverges too. All right. So that is the limit comparison test. That wraps up my lecture for today. I will be available tomorrow night for my virtual office hours, 6 to 9. You'll be able to log on and interact with me and ask me questions, and I can write out answers on the whiteboard like this. I should be getting even better equipment. I know the handwriting's a little rough, kind of because I bought a cheap writing pad for myself, but the department should be getting me better equipment in the near future So hopefully the quality of these videos will improve. And as I said, feel free to continue using whatever resources you want, whether it's my colleague Ariel's videos or any other YouTube content out there. Do whatever you need to do to learn the material. Okay, feel free to message me with any questions and I'll get back to you with a hopefully helpful answer. Let me know if you have any questions. Thank you.